Okay, this is the second part of section 8.4. We're still dealing with vectors. We just finished talking about unit vectors. Now let's talk about dot product. Dot product. Okay, so we've done some operations with vectors. In the previous video, we added vectors. When you add two vectors, the sum is called the resultant, and the resultant is another vector. When you subtract vectors, the subtraction of two vectors yields another vector. We had another operation with vectors called scalar multiplication. Scalar multiplication. Let me go to these operations up here. So we had addition of vectors and subtraction of vectors. We add them and subtract them component-wise. And the result is another vector. We had scalar multiplication of vectors. Scalar multiplication of vectors was a scalar, a real number, times a vector. And well, what you do is you multiply the scalar times the first component, the x, the horizontal component, the scalar times the vertical component. And the result is another vector. So those are the two operations that we have done with vectors: scalar multiplication, addition, and subtraction. Now we have a new operation of vectors. It's called the dot product. And let me just give you the definition right now. So the dot product of the vectors u and the vector v is denoted u dot v, and you read this as u dot v, and it's given by, so you have u dot v equals ac plus bd. Notice what's going on here. So from my vector u, what I'm doing is I'm grabbing the horizontal component, and I'm grabbing the horizontal component from my vector v, and I multiply those two things. That's AC right there. Plus, and then the product of the vertical components, BD. And that is my dot product. Yeah? So this is just the definition of the dot product. We'll think about what this means here in a second, but let's just kind of start using this right now. Notice that the dot product of two vectors is no longer a vector. So the output of the dot product is not a vector. It's a real number. It's a scalar. Earlier, when we added vectors, the result was another vector. Now, if you do the dot product between two vectors, the result is no longer a vector. This is not a vector. This AC plus BD thing is just a number. It's just a scalar. Okay, so just be aware of that. Let's find some dot products. So at this moment, pause the video and try to answer these two questions here. See, I don't know, give yourself 5-10 minutes, see if you can find the dot product between u and v and the dot product of m and n. Okay, so let me find the dot product u and v. Well, the dot product is just going to be -2 times 3. So the x component or the horizontal component times the horizontal component plus, and then the vertical component times the vertical component. 4 times 5. Okay, well, whatever this value is. So that's -6 plus 20. So 14. What does that mean? What does it mean for the dot product of two vectors to be 14? That's what I would be asking myself right now. We'll answer that question in a second. Let's just learn how to find the dot product first. All right, so that's it. That's the dot product for UV. Hopefully we agree on the answer here. Okay, let's find the dot product of m and n. So m dot n. All right, well, same situation. Is just going to be 9 times 3 plus -4 times -5. Okay, well, that's 27 plus 20. So 47. What does it mean for the dot product to be 47? All right, so we'll answer this question, what the dot product means here in a second. Hopefully right now you are comfortable computing the dot product between two vectors. Remember that the dot product, keep in mind that the dot product is not a vector anymore. It's just a number. It's telling you something about the two vectors that you started with. All right, so now let's see. What does the dot product mean? So the dot product of two vectors can be negative. You can get a negative number. It could be 0, or it could be a positive real number. So your dot product can be negative, can be 0, can be positive. Well, what does it mean to be negative? What does it mean to be 0? What does it mean to be positive? Okay, well, the dot product tells us about the angle between the vectors. So that's kind of nice. Now we have a tool to determine an angle between two vectors. That's what the dot product is good for. All right, this is just a little bit of motivation for the next formula. There's another way to compute the dot product that involves angles, the angle between the vectors. All right, consider this little ugly sketch here. I have two vectors. I have the vector u in red. I have the vector v in green. Vector u has, this is its horizontal component, that's its vertical component. Vector v has this horizontal component, that vertical component. And then I have this other vector u minus v. U minus v is this diagonal. U plus v would have been the longer diagonal of this parallelogram. That would have been the sum. Right now I'm dealing with u minus v. Another consideration here is let's keep the angle theta to be bigger than or equal to 0 and less than or equal to 180. Let's find theta in this picture. Let me try to find theta in this picture. So theta right now, I guess, is just the angle between the vectors u and v. So I am trying to find the angle between the vectors u and v. Okay, so how would you do this? How would you find this angle? What tools do we have at our disposal? I mean, if this was a right triangle, maybe we could use some trigonometry. But this is not a right triangle. So what tools do we have for non-right triangles? The two tools that come to mind are the law of sines and the law of cosines. And if you think about it right now, I'm trying to find this angle theta. I know, do I know the length of the vector u? I do know the length. The length of the vector u is just its magnitude. Do I know the length of the vector v? I do. The length of vector v is the magnitude of v. I also know the magnitude of this vector in blue, u minus v. It's just its magnitude. So I know the lengths of this triangle. I need to find this angle right here between these two vectors. All right, and I think the tool that we're going to need here is the law of cosines. So the law of cosines is going to be helpful to determine this angle theta. What does the law of cosines say according to this picture? Well, it says that the length of this opposite side, so that's the magnitude of u minus v squared, equals the magnitude of u squared plus the magnitude of v squared minus 2 times the magnitude of u, magnitude of v, cosine of the angle opposite. All right, and now I'm gonna wanna solve for theta, or get to, as much as I can solve for theta here. All right, so now what's the magnitude of u? The magnitude of u, if you think about it here, I'll put a little thing. So the magnitude of u, just by definition, is supposed to be the square root of a1 squared plus a2 squared. Same thing for the magnitude of v. It's just that this would be square root of b1 squared plus b2 squared. What's the magnitude of u minus v? And well, u minus v, if you think about it, is just the vector a1 minus b1, comma, a2 minus b2. So the magnitude of that vector. So right now I'm just literally using the definition of magnitudes here. The magnitude of u minus v, it's this square root, and this is being squared, equals the magnitude of u is this square root, and then things are getting squared. That's why I put brackets around things. Plus the magnitude of v, and that's this squared, minus 2 times the magnitude of u, v cosine. This magnitudes right here I'm keeping small just for the sake of space. And also because I want them to be in the last formula that we're going to develop. Alright, so these square roots and the exponents cancel each other out. And then if you actually FOIL a1 minus b1 squared, so think about a1 minus b1 squared. If you actually were to multiply that out, that becomes a1 squared minus 2 a1 b1 plus b1 squared. Those three terms right there is this being squared. Then plus, then we have to square this. Well, it's something similar. a2 squared minus 2a2b2 plus b2 squared. All right, and then all of this is equal to, here the square root and the exponent cancel each other out, so there's no need to square here. That's just a1 squared plus a2 squared plus b1 squared plus b2 squared minus da 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 da. Now I'm trying to solve for cosine. I remember our goal is to solve for theta, so I'm trying to isolate theta as much as I can. So from the right hand side I subtract a1 squared, a2 squared, b1 squared, and b2 squared. So I get rid of these four terms right here by subtracting them, and I subtract them from both sides. And if you notice, they cancel on the left hand side. And so then what I have, once things cancel, is this expression right here with negative 2's throughout. Well, I'm going to divide everything by negative 2. And if I do that, I end up with this expression right here. And guess what? There's this part on the left hand side. That a1 times b1 plus a2 b2, that's just the dot product of u and v. That's just the dot product of u and v. That's just the definition of the dot product. So instead of writing it like that, I'm going to say u dot v equals magnitude of u, magnitude of v, cosine of theta. Here now what I'm going to do is divide by this product of magnitude of u times magnitude of v. So I have that u dot v divided by magnitude of u, magnitude of v. So it's the dot product of u and v divided by the product of the magnitudes of the vectors. That's equal to cosine theta. And this, at this point, I guess, you know, the last thing would be here to, in order to really solve for theta, would be to take cosine inverse. But I'm going to leave it like at this point. I'm going to leave it like that. This is another definition of, this is the geometric interpretation of the dot product. Because now remember, theta is the angle between those two vectors that we started with, u and v. And this is true no matter what vectors you're dealing with. Now remember, our angle theta was between 0 and 180. And now what I know is that cosine of theta can be positive in quadrant 1. That's between 0 and 80. It can be 0 at 90 degrees or on the y-axis. Cosine of 90 degrees is 0. Cosine of pi over 2 is 0. So on the y-axis my cosine is 0. Or it can be negative. Cosine is definitely negative in quadrant 2. That's if my angle is obtuse. Alright, so then let's think about this. Let's put all of this together. So what this is saying is that if the dot product happens to be some value positive, then the angle between the vectors is acute. If the dot product happens to be 0, then you're dealing with vectors that are perpendicular. The angle between my vectors is 90 degrees or pi over 2. It's a right angle between my vectors. That's if the dot product is 0. If the dot product between two vectors is negative, that says that the angle between the vectors is obtuse, less than or equal to 180 and bigger than 90. So that's some part of the usefulness of the dot product. It allows us to know what is the angle between two vectors. And an important sort of result from all of this is that two vectors are perpendicular if their dot product is 0. If their dot product is 0, then two vectors are perpendicular. And perpendicular vectors are also called orthogonal. So if you see this word orthogonal, that just means perpendicular. It means that the angle between my vectors is 90 degrees. It means that the dot product is 0 of these two vectors. Alright, so the two things that are important right now is this definition, this interpretation of the dot product. This is worth keeping in mind. Another thing worth keeping in mind is just the definition of dot product. Another thing to keep in mind is just the definition of dot product. So this is also worth keeping in mind. Alright, let's see, let's get into some exercises here. Let's do this exercise. Let's find the angle between U and V. Yeah, and if I was you, I'd pause this video here for, I don't know, 5-10 minutes and see if I can solve this on my own. I want to find what is the angle between U and V. And let's I'm going to say here in degrees. Just to make things easier. Although it doesn't matter. Sorry, coffee break. Okay, so hopefully you've paused the video, you try this on your own. Let's find the angle between these two vectors. So I am going to use this fact about dot product, that we said that U dot V divided by magnitude of U magnitude of V, that's equal to cosine of theta. That's what I want to use in order to find the angle between my vectors. Theta is what I'm after. So let me kind of fill in some values here. So I need to compute a couple of things, 3 things. U dot V first. Okay, what's U dot V? According to my angles here, well, that's supposed to be 5 times -1 plus 4 times 5. Alright, so I'm just computing the dot product. Why am I computing the dot product? Well, because I need it up here in this numerator. So that's -5 plus 20. -5 plus 20 is 15. Okay, now let me compute the magnitude of U. Okay, so I gotta compute the magnitude of U. The magnitude of U is going to be 5 squared plus 4 squared. Alright, so that's the square root of 25 plus 16. Well, that's the square root of 41. 41 is a prime number, so I don't think we can do much with that radical. Alright, I need to compute the magnitude of V. Well, the magnitude of V is -1 squared plus 5 squared. Alright, so that becomes 1 plus 25. Which is the square root of 26. 26 is just 2 times 13, so there's no perfect square, so that's all we can do there. Alright, so that's just my preliminaries. That's just kind of my scratch work. Now let me put everything together. Now I have that 15 over square root of 41 times square root of 26 is equal to cosine of theta. Literally, I'm just using this in geometric interpretation of the dot product. I filled in what the dot product was, what's the magnitude of U, what's the magnitude of V. That's my work for that. And now this is going to help me find the angle between my vectors. So I think the last thing I gotta do is take cosine inverse of this expression. Cosine inverse of 15 over the square root of 41 times the square root of 26. That's my theta. Now I am going to, we said that we were agreeing to have our calculator in degree mode, and let's just round to the nearest tenth. So let's just round to the nearest tenth. Let me punch this into my calculator. So cosine inverse of 15 divided by square root of 41 times 26 hang on, I made a mistake. Cosine inverse of 15 divided by square root 41 square root 26. Alright, I get about 62.7 degrees. Once I round to the nearest tenth. 62.65 something degrees. Alright, I hope that you agree with this. I hope that we agree, we have some consensus on this answer. And hopefully you tried it on your own. Remember, all of these little examples are worked out in red. And so then you can pause the video and go back, whatever you need to do to find details. But definitely try to do these examples on your own before you just jump into the steps of working out the problem. All right, some applications of vectors. Well, there's a lot of applications of vectors. They're very useful in physics, in statics, engineering. It's a lot of vectors. They have a lot of use. We're going to talk about a couple of little applications here. I'm just going to go through the first two examples in the notes, and that's it. So there is a special type of vector. It's called the equilibriant. And the equilibriant, what it is it's the counterbalance to a resultant of vectors. Remember that the resultant is the sum. So if I have vector u and I have vector v, the sum is this diagonal vector, the diagonal that joins the parallelogram. So that's my resultant. And while the equilibriant is just pretty much the same length as the resultant, it just points in the opposite direction. That's why it's called the equilibriant. It's just a counterbalance. Okay, so let's see. Let's find the equilibriant of forces 28 newtons and 60 newtons acting on a point A if the angle between the forces is 50 degrees. Okay, so we're supposed to find the equilibriant. We're supposed to find the magnitude of the equilibriant if there are two forces of 28 newtons and 60 newtons acting on a point A and the angle between these two forces is 50 degrees. If you're brave, pause the video, try to see if you can come up with some answers on your own. If not, then let's take a look at how we can work this out. Alright, so let me begin by sketching. So I have a point A. And that's my point A. I have two forces acting on this point. I have one force, I don't know, doesn't matter which way I draw it, going that way. I have some other force maybe going this way. Yeah, I don't know. This force is supposed to have, I don't know, I'm gonna call it U. This other force, I'm gonna call it V, just to kind of put some names on things here. Okay, they told me that one of the forces was 28 newtons. That's talking about the magnitude of my vector. So then I'm going to agree over here that the magnitude of U is 28. So the length, think about it as the length. The length of U is 28. The length of V is going to be 60. Remember, a vector has both a magnitude and a direction. So right now, when they're talking to us about this 28 newtons and 60 newtons, that's dealing with the magnitude. All right, they also told me that the angle between the forces is 50 degrees. All right, so that's kind of what my picture looks like. I have these two vectors acting on a point. The magnitude of one of the vectors is 28, the magnitude of the other vector is 60. And right now, what you want is you want to find the magnitude of the equilibriant. Well, in order to find the magnitude of the equilibriant, you're first going to have to find the resultant, or the sum. Because the equilibriant, so let me sketch out what's going on. So we're going to have to find first the sum. And let me draw it in another color. So I am going to first have to find, so that right there, that's u plus v. Let me draw it in red. This is u plus v. Yeah, that is called the resultant. Well, right now we're not interested in the resultant. What we're interested in is the equilibriant. So the equilibriant would be this vector. Yeah. Right now our goal is to find the magnitude of the equilibriant. This green one is my resultant. Yeah. So the resultant is u plus v. So first of all, we gotta find that vector u plus v. How do we find this vector u plus v? Think about what was given to us. We have a parallelogram. We want to find the length of the diagonal. If you remember in the previous section, in the Law of Cosines, in section 8.2, we had some exercises kind of like this. We were given a parallelogram and we were asked to find the diagonal, both diagonals. How do I find this diagonal of this parallelogram? Let me remind you, this angle of 50 and this other angle over here should be equal. This angle right here and this angle should be equal, and the sum of the interior angles of a parallelogram are up to 360. So if this is 50 and this is 50, that's 100 degrees. Then that means that this should be 200, and so this angle plus this angle should add up to 260. So, and then we have to split them in half. So hopefully you agree with me that this angle right here should be 130 degrees. Hopefully you agree with that. So if this is 50, so 50 plus 50 is 100, 130 and 130, that's 260. 100 plus 260 is 360. Okay, so now what? How do I find, right now I'm interested in the length of this green vector. How do I find the length, the magnitude? So right now what I want to find is the magnitude. The magnitude of the resultant. So, law of cosines. This law of cosines, so useful. Alright, so what does the law of cosines say in this case? Well, it says the following. It says, think about this triangle right here. So, this side opposite squared equals this side squared plus this length squared minus 2 times this length times that length cosine of this angle. That's what the law of cosines would say. So let's set that up. Let me just give myself a little bit of room here, sorry. Okay, so the law of cosines, according to this picture, says the following: that u plus v squared is equal to u squared plus v squared minus 2u times v cosine theta. Now it's just a matter of filling in what we know here. So this is what I'm after. I am after the magnitude of the resultant. I know what the magnitude of u is. It's 28, so 28 squared plus, then this guy is 60 squared minus 2 times 28 times 60 cosine theta. Okay, so some arithmetic here. I get the following. I get 4,384 minus 3,360 cosine theta. Well, I know what theta is. I know what theta is. I should have just written that out. It's 130 degrees. Okay. Make sure your calculator is in degree mode. Now I have this 4384 minus 215.9766. So then finally I have that the magnitude of the resultant squared is equal to 4,599.97666. And then I need to take a square root. So the square root of this gives me about 67.8 newtons. All right, so what we have done is we have found, so let's think about what we've done here. We had two forces acting on a point A. Our point A is right there. That's our point A. We had the force U and a force V. The magnitude of U was 28. The magnitude of V was 60. We're interested in the equilibriant force. The equilibriant is this vector in black. In order to find the force of the equilibriant, we have to find the force of the resultant, because the equilibriant and the resultant in a sense have the same magnitude. They just point in opposite directions. So we had to find the magnitude of the sum. In order to do that, we used the law of cosines. We looked at this little picture here. We had to think about, what's this angle here? How did we conclude that this was 130 degrees? Then we use the law of cosines, and we conclude now that the resultant force is 67.8 newtons. That means that the equilibrium force is the same. The equilibrium force is equal to 67.8 also. Well, newtons. I hope that you agree that both of them are, the force is the same. What's different is the direction. Yeah, I mean, this guy would be negative, this guy would be positive, but their magnitudes, their lengths are the same. Yeah. All right. So hopefully this question is okay. Let's move on to the last example in this section. This application problems sometimes get a little bit cumbersome. There's some details involved here, especially with force and mass and some physics. All right, let's think about this next example. Okay. Again, if you're brave, pause the video and take a few minutes and see if you can answer it yourself. I'm sure you can. Do it. Try it. What we want to do now is we want to find the force required to keep a 3,000 pound car parked on a hill that makes an angle of 15 degrees with the horizontal. This is a weird problem. This problem requires a little bit of care here. Why? Well, let's see. Let me begin by sketching what I sort of see here. So I think a sketch is always a good starting point. I am going to sketch what I understand. And this is what I understand right now, that this is 15 degrees. Okay. So I have some incline. Okay. Somewhere along here, there's a car. I'm just going to indicate it by a point. Yeah. Let's just pretend that right there is a vehicle at that point. Yeah. And well, there's a couple of forces happening here. There's this force going in that direction. That's what the 3,000 pounds is talking about. And that wants to go downhill. But then there's another force. There's another force going down this way. Yeah, there's this other force going down this way. I'm gonna call it force. I don't know, because I have no idea what it is, and this is going to make a 90-degree angle right there. And it's this force, it's this vertical force right here that's keeping my vehicle in place. So this vertical line down here is what's keeping the car from rolling down the hill. Yeah, so let's say that. So F is the force keeping the car from rolling downhill. Okay. I want to find that force. That's what's being asked of me. Find that force, the one that keeps the car in place. All right, now we got to talk a little bit about physics. And the first thing I got to tell you is that, well, pounds is a measure of mass. Not force. So I'm going to have to, in a sense, translate my pounds into force. So we need to do some conversions here, which is kind of unfortunate. So we need to convert to force. So pounds to force by first converting to kilogram. And then converting to newtons. All right, And so in a sense right now what I'm trying to do is I'm trying to express this 3,000 pounds as a force in newtons. That's what I'm trying to do. So I'm gonna have to Google a couple of things. I'm gonna have to Google how many kilograms there are in a pound, and then I'm gonna have to figure out the conversion between newtons and kilograms. So let me sort of begin here. So I'm gonna say mass. So right now we were given mass, and it's 3,000 pounds. I'm gonna multiply that by 0.454. That's, I googled that, and this is kilograms per pound. That's how many kilograms there are in a pound. So my pounds units cancel, and so 3,000 times 0.454 gives me 1,362 kilograms. Okay, now Newton's second law. Says that the force is equal to my mass, which in this case right now is 1,362 kilograms, times this gravity, this acceleration, the constant acceleration of gravity on the surface of the Earth, which is 9.8 newtons per kilogram. Okay, so the kilograms here, let me put this in parentheses instead. The kilograms here cancel, and I end up having to multiply 1,362 times 9.8, and that gives me 13,347.6 newtons. Now this is a force. This is a force. So I'm not dealing with pounds anymore. So this 3,000 pounds that we had earlier, we could also say 3,000 pounds is the same thing as 13,347.6 newtons. That's my 3,000 pound car. That's how much force that's the force that wants to roll down the hill. Alright, so we haven't really done anything yet. We haven't even gotten to the point where we want to solve this. What is the question here? The question is, we want to find the force that's keeping the car from rolling downhill. Right now what we did is we figured out what's the force that wants to make the car roll downhill. But then there's another force, the one that's keeping it in place. We said that that force is this vertical vector going down. That's the force that's keeping my car parked right there on that hill. So what I need to do is find the magnitude of that force. How are we going to do that? I don't know, look at this picture. It's a right triangle. I want the length of this vertical line. And you know the hypotenuse of this right triangle. So what trigonometric function do you think works well here? I would say sine. Sine of 15 degrees involves my opposite over my hypotenuse. Those are the things I want to play with. So let me write that down here. So I'm going to say that sine of 15 degrees is going to be my force divided by, I'm going to say that I'm dealing with forces here, so I don't want to write the 3,000 pounds. I'm going to write 13,347.6 newtons. Okay, now let me solve for F. Alright, so then that's 13,347.6 times sine of 15 degrees. That is F. And let me punch this into my calculator, making sure to be in degree mode. And I conclude then that the force required to keep the car in place is 3,454.6 newtons. Interesting. The force pushing it, making it roll downhill is 13,000 newtons. The force required to just keep it in place is 3,000 newtons. Why is that? Oh, physics. All right, so that's it for 8.4 vectors. So the next video will be jumping into 8.5, polar form of complex numbers. All right, so thank you, and I'll see you in the next video.